Good day, class. Today we're going to continue on with Unit 2. As I said at the end of the last video, this is going to be a very short unit. This will be the last lesson that covers everything that's going to be on this unit test. So we'll go ahead and get going. We're going to use long division to divide polynomials. We'll use synthetic division as well. We'll talk about the remainder and factor theorems. We'll talk about the rational zero test. And we will also talk about Descartes' rule of signs. All right, so long division of polynomials. So consider the graph of f of x equals 6x cubed minus 19x squared plus 16x minus 4, right, which we can see down here. All right, so notice that x equals 2 appears to be a 0 of f, because f of 2 equals 0, right? And from the scaling here, each one of these is 1/2, right? So 2 would be right there. You know that x equals 2 is a 0 of the polynomial function f. So if we know that, then we know that x minus 2 is a factor of f of x. Right, this means that there exists a second degree polynomial q of x, such that f of x equals x minus 2 times the q of x. All right, so to find the q of x, we can use long division of polynomials. So we'll go ahead and do that. We're going to divide 6x cubed minus 19x squared plus 16x minus 4 by x minus 2. And then it wants us to use the result to factor the polynomial completely. All right, so we kind of set it up just like long division, right? Like we used to, way back in 4th grade or whenever. All right, so we say x minus 2 is going into 6x cubed minus 19x squared plus 16x minus 4. Okay, so essentially, we're going to kind of just ask ourselves the same question over and over and over again, all right, and kind of run through the same steps, all right? So with the question I ask myself is I look at my leading term here. I don't really care about the whole thing in general, just the leading term. So in this case, x. And I say, what do I need to multiply x by to get 6x cubed? All right, well, x times 6x squared would be 6x cubed. So I'm going to put 6x squared up here, and I just put it above the same term, the x squared. That's why I put it over there. All right, once we do that, we take this number and we distribute it by my entire divisor. So we get 6x cubed minus 12x squared. Okay, now what we have to be careful about with what we're doing here is we're subtracting, all right? It's very, very important that you remember that we're subtracting. If you want, you can change the sign of both of these things and add. A lot of students like to do that because adding is a lot easier than subtracting, right? But if we subtract, we say this minus this cancels, which is what we want, right? That's the whole reason of why we picked it. And negative 19x squared minus negative 12x squared, that is going to be negative 7x squared, right? Because when you subtract a negative, you're really adding. It's really negative 19x squared plus 12x squared. All right, then we go ahead and bring down our next term, and then we do the exact same thing over again. We say, okay, what do I need to multiply this by to get this? All right, well, that would be negative 7x. Again, I take what I just wrote up here, my negative 7x, I distribute it by my entire divisor. So I'm going to get negative 7x squared plus 14x. Again, I am subtracting. This minus this cancels out. All right, 16x minus 14x is 2x. I go ahead and bring down my next term of minus 4. Then I start all over. I do the same thing again. What do I need to multiply x by to get 2x? Well, just 2. So I put plus 2 here. Then I go ahead and distribute. I get 2x minus 4. This cancels, this cancels. Awesome. That means there's no remainder. That means that this thing divides in perfectly. Okay? So as of right now, I know that my entire f of x here, right, if this thing is f of x, then I know that f of x is now equal to x minus 2 times 6x squared minus 7x plus 2. Okay, now it wants me to factor this thing completely. So I need to see if this is factorable. All right, I'm going to do that off to the side down here. All right, so you can use whatever factoring technique you want. I use what's called the trash can method. All right, where I put a P and an S up here. P stands for product, S stands for sum. All right, underneath P, you put A times C. You don't really have to write A times C. I just do that for explanation purposes. And a quadratic, right? This is a quadratic equation here. We say ax squared plus bx plus c. So a is my 6, 2 is my c. All right, so 6 times 2 here is 12. Underneath my S column, I put B. Again, you don't need to write it. It's just there for explanation purposes. My B in this quadratic is negative 7. So I put negative 7 here. All right, so I need to find two numbers that multiply, their product is 12, and that add to get their sum of negative 7. Those two numbers are negative 4 and negative 3. Right? Negative 4 times negative 3 is 12, and negative 4 plus negative 3 is negative 7. All right? Once we have those two numbers, I keep my leading coefficient here of 6. All right, so I say 6x and 6x. I have two blanks here. I fill in the blanks with the two numbers that I just found. So minus 4 and minus 3. If one or both of them were positive, these would be pluses instead of minuses. Okay, now this is called the trash can method because I have extra stuff in here. Okay, obviously, if I just multiply these two things, I'm not going to get this, right? 6x times 6x is 36x squared, not 6x squared. It's called taking out the trash because I take out the extra stuff that I don't need. So what we do is we look at both of these factors individually, and we ask ourselves, can I pull out a greatest common factor? So can I pull something out of 6x minus 4? Yes, I can. I can pull out a 2. And when I do that, I'm left with 3x minus 2. Can I pull something out here? Yes, I can. I can pull out a 3. And when I do, I'm left with 2x minus 1. It's called taking out the trash because whatever we just pulled out, we throw away. Now this is my factorization. All right. So I have x minus 2, and then here I have 3x minus 2 and 2x minus 1. I'm done. All right, this thing is now completely factored here. And we are done. Okay, so let's try this again. All right, so I'm saying x plus 3 is going into x cubed minus 2x squared. Notice that there's a missing linear term, right? There's no something x. If you want, you can put 0x in there, right? With long division, you don't have to. It can help you, but you don't have to. When we get to synthetic division, you have to. Okay, so If you just want to do it just to get in the habit of putting it in there, then that's fine. All right, so we keep going through those same steps again. What do I need to multiply this by to get this? Well, that is x squared. When I distribute, I get x cubed plus 3x squared. Remember, I am subtracting. All right, so x cubed minus x cubed is 0. Negative 2x squared minus 3x squared is negative 5x squared. I can bring down my next term. I start all over. What do I need to multiply this by to get this? Well, that would be negative 5x. So now when I distribute here, I get negative 5x squared, which is what I want, and minus 15x. Again, remember that I am subtracting, so anything minus itself is gone. All right, 0 minus negative 15 is the same thing as 0 plus 15, so this becomes 15x. I can bring down my minus 9. All right, I ask myself again, what do I need to multiply this by to get this? That is just a positive 15. When I distribute, I get 15x plus 45. Again, remember I am subtracting. These will cancel. Negative 9 minus 45 is negative 54. This is my remainder. Okay, so we're not really going to be able to factor this quite as nicely as we did our last one. All right, but we know that this is going to be x plus 3. And then I'm going to have x squared minus 5x plus 15. And how we deal with remainders is, since that's a minus 54, we can say minus 54, and you always put that over whatever our divisor was. So in this case, x plus 3. And we're done. We can't factor this any further because of this messy remainder and stuff. So we are done. All right, we can try this again. All right, so now I'm going to say 2x minus 1 is going to be going into 8x cubed. All right, now we're missing a squared term and a linear term, so if you want to do this, that's perfectly fine. Like I said, with long division, you don't have to. It just kind of makes things a little bit easier as far as the steps that we go by. All right, so now we go ahead and ask us the same questions here. So what do I need to multiply this by to get this? All right, that would be 4x squared. All right, so if we distribute this, we're going to get 8x cubed, which is what we want, minus 4x squared. All right, so I'm subtracting here, remember? So these will cancel. 0 minus negative 4 is positive 4. And I can bring down my 0x. What do I need to multiply this by to get this? That would be 2x. If I distribute, I get 4x squared, which is what I want, minus 2x. All right, so that will cancel. I can bring down, go ahead, 0, and remember we're subtracting here, so 0 minus negative 2 is 2x. We bring down our minus 1. I need to multiply this by 1 to get this. And when I distribute, we get 2x minus 1. No remainder. Very nice. All right, so now my f of x is going to equal 2x minus 1 times 4x squared plus 2x plus 1. All right, you can check and see if you can factor this, right? So we could do our p and our s. So a times c is 4, s is 2. All right, are there any numbers that multiply together to give us 4 and add together to give us 2? All right, well, the only options are 1 times 4 and 2 times 2. And of course, you could make both of these negative as well. But 1 plus 4 would be 5. That doesn't match. 2 plus 2 would be 4. That doesn't match. Same thing with negatives. If all of these were negative. Negative 1 plus negative 4 would be negative 5. That doesn't match. Negative 2 plus negative 2 would be negative 4. That doesn't match. So since it's impossible, this thing doesn't factor. So we're done. That is our complete factorization. Now, this would also be a good time to bring up this 8x cubed minus 1 is a difference of perfect cubes, right? We talked about difference of perfect squares. There's also a factoring technique for difference of perfect cubes. So if you have a cubed minus b cubed, all right, that is equal to a minus b times a squared plus ab plus b squared. All right, then also there's a difference, or I'm sorry, sum of perfect cubes. There's not a sum of squares because it doesn't work with even powered things, but with odd it does. So a cubed plus b cubed is very similar. So a plus b times a squared minus ab plus b squared. All right, so here we could actually rewrite this as 2x cubed minus 1 cubed. All right, because 2x times 2x is 4x squared. Multiply it by 2x again, you get 8x cubed. So that works. And then, of course, 1 cubed is 1. All right, so we could actually factor this using this formula, right? Everywhere you see an a, you put a 2x. Everywhere you see a b, you put a 1. So you would get 2x minus 1. 2x quantity squared, 2x times 2x would be 4x squared, plus 2x times 1 is 2x, plus 1 squared is 1. Right? Well, that's exactly what we got here, right, doing long division. Had you noticed that this was a difference of perfect cubes and you remembered how to actually factor them, then you wouldn't have needed to go through long division. All right, but it's a good practice for long division, and I'm sure that next to nobody remembers these two formulas. But you definitely will want to write these down somewhere. All right, these will come in handy over the next couple of units. So again, factoring, very, very important in this class. All right, so divide this polynomial here by x squared plus 2x minus 3 and use the result to factor completely. All right, well, we don't like this because it's not in standard form. All right, so I'll go ahead and put it in standard form, but x squared plus 2x minus 3, dividing it into here. And I want to say that there's a typo that makes this really messy, if I remember this correctly. I think we want to change the sign of one of these. So give me a minute to work through it, and I'll tell you if that is correct or not. Of course, we can always go through the steps. Okay, so what would I need to multiply this by to get this? 2x squared. All right, and then if I do multiply that, we would get 4x squared plus 4x cubed, and then minus 6x squared. Remember, we are subtracting. Oh, wait a minute. Sorry, I obviously made that mistake there. There should be a 2. All right, so when we subtract here, these will cancel, these will cancel. Negative 5 minus negative 6 is positive 1, so this just becomes x squared plus 3x minus 2. All right, so what do I need to multiply this by to get this? That would just be 1. When I distribute, we get x squared plus 2x minus 3. Again, we are subtracting, so these cancel. Here we just get x, and we get plus 1. All right, so that's fine. This is just my remainder. So if I wanted to factor this thing, x is going to equal x squared plus 2x minus 3 times 2x squared plus 1 plus x plus 1 over x squared plus 2x minus 3. When it wants us to factor completely, we can actually factor this. So this will just be x plus 3 and x minus 1. And then we have all of this stuff again. 2x squared plus 1 plus x plus 1 over x squared plus 2x minus 3. So this is my complete factorization. Right, now we're going to use synthetic division. Right, you can use synthetic division whenever your divisor is of the form x minus c. So in this case, my c would be -3, right? Minus a -3 would become +3. So you don't want to use it if you have like 2x minus 7 or 3x plus 2. Really, you only want to use it if we have that form. All right. How we do synthetic division, right? We start with a box. We put the 0 of this in the box, right? So if we set that equal to 0 and solve, we would get x equals -3. So we put -3 in the box. We take all of my leading coefficients and we write them out here. If there is a missing term, we're missing a cubic term, right? We go from fourth to second. You have to put a 0 in. So my leading coefficient here is 1. I'm missing a cubic term, so I would put 0. Then I have -10, then -2, then 4. I leave some space and I draw a line. I bring my first number down always. I multiply what's in my box times what's down here. -3 times 1 is -3. I put that number up above the line. Then I'm going to add. So 0 plus -3 is -3. Then I'm going to multiply again. So -3 times -3 is +9. Then I'm going to add. -10 plus 9 is -1. Then I'm going to multiply again. -3 times -1 is +3. Then I'm going to add 1. I'm going to multiply again. -3 times 1 is -3. I'm going to add again 1. All right, this is my remainder. All right, now this is going to be my quotient. All right, so this divided by this is equal to, these are my coefficients of my quotient. All right, and we start with 1 power less than whatever my original function was. So since this was a 4th degree polynomial, this would be 1x cubed minus 3x squared minus 1x plus 1. And then my remainder always still goes over my divisor, right? So we say plus 1 over x plus 3. So this is my divisor. They didn't ask us to factor, or we would have said this times x plus 3. All right, so let's use synthetic division again. All right, so here x minus 3, the 0 of that would be +3. So that's what goes in my box. I have 5, 8, negative 1, 6. There's no missing, right? I go from 3 to 2 to 1 to none. So there's nothing missing. I bring my 5 down. I multiply. I add. I multiply. I add. This is messy, right? But I multiply. That's going to be 180 and 24. So 204. And 230. If I did that correctly. 1, 6, right down. 15, 23, 69, Right, that looks good. So, of course, this would be 5x squared plus 23x plus 68 plus 230 over x minus 3. Done. All right, the remainder theorem. All right. So if the polynomial f of x is divided by x minus k, so that's, we can use synthetic division for that, then the remainder is f of k. Right? So basically whatever the remainder is, if we took this number and plugged it into the function, that's what we would get. Right? So the remainder theorem tells you that synthetic division can be used to evaluate a polynomial function. To evaluate a polynomial function, f of x, when x equals k, we divide f of x by x minus k. The remainder will be f of k. This sounds a little complicated, much, much easier, right, than what it sounds like, and I'll show you here. Use the remainder theorem to evaluate this function at x equals negative 2. Okay, now when they give us the 0, that is actually what goes in the box. All right, so don't put the opposite, right, because they didn't say divide it by x minus 2, right? This is actually dividing by x plus 2, all right? So now I put all of my coefficients, 3, 8, 5, negative 7. All right, I bring my 3 down, I multiply, I add, I multiply, I add, I multiply, and I add. The remainder theorem tells me that f of negative 2 is equal to this number. Okay, now obviously with something like this, we could have easily just plugged negative 2 in for x, all right? But if you don't have a calculator, this way actually might be a little bit easier. And if you have way more complicated functions, then it's definitely going to be easier, okay? So that's all the remainder theorem says. Guys, on a test, your directions are going to say, use the remainder theorem. That means you have to do it this way. If you just plug negative 2 in and write down an answer, you're going to miss all of the points for the work. Okay, so be very mindful of that. All right, so let's do it again. All right, here would be a good spot for you to practice. I would hit pause on this video and try this yourself. All right, again, it's very easy to plug negative 1 in here. Don't do it. If it tells you to use the remainder theorem, you must use the remainder theorem. All right, so I'm trying to find negative 1, f of negative 1, so I'll put that in my box. Here I have 4, 10, negative 5, negative 8. Bring my 4 down, multiply, add, multiply, add, multiply, add. All right, so this is my remainder. So f of negative 1 is equal to 3. Very straightforward. All right. Okay, the factor theorem. The polynomial f of x has a factor x minus k if and only if f of x equals 0. So this is kind of an extension of that remainder theorem, right? If there is no remainder, if my remainder is 0, that means that that thing divides in evenly and thus is a factor. All right? So show that x minus 2 and x plus 3 are factors of this thing. Okay, so I'll start with x minus 2. Here they do give me the factors, so I put the opposite in my box. All right, I have 2, 7, negative 4, negative 27, negative 18. All right, so go ahead, bring this down, multiply, add, multiply, add, multiply, add, multiply, add. So since this was a 0, since there's no remainder, that means that this divided in evenly and thus is a factor. Now, to show that x plus 3 is a factor, you could start all over, use these exact same numbers, and just put a negative 3 in this box. But you can actually just kind of ignore this now and use these. That's perfectly fine. So I can bring this 2 down. We will get negative 6. We add, we multiply, we add, we multiply, we add. Boom. All right, so since this is a 0, we know that this is a factor. Now, if we wanted to get really in depth here, they didn't ask us to do this, but this thing can now be factored to x minus 2, x plus 3, and this would be 2x squared plus 5x plus 3, right? So this is now factored out this way, right? We could actually probably factor this as well, right? I can use my trash can method. 2 times 3 is 6, and we have 5. All right, so 2 and 3, right? 2 times 3 is 6, 2 plus 3 is 5. Keep my leading coefficient, so 2x plus 2, 2x plus 3. See what I can factor out. I can pull a 2 out here. I can't pull anything out here, so it stays. I throw away whatever I pulled out. This is my factorization. Again, right? They did not ask us to do this, but had they said factor completely, all right, we did. And even furthermore, we could find all the zeros of this function, right? Easily set each one of these equal to 0 and solve. Right? But that's a little bit more than what they asked, but just for future reference. All right, so show that x equals negative 3 is a 0 of x cubed minus 19x minus 30. Then find the remaining zeros. All right, so here they give us the 0, so that's exactly what goes in my box. Remember, if they give you the 0, put it right in. If they give you the factor, you have to find the 0 and put it in. All right, my coefficients, 1, I'm missing a squared term, so I have to put 0 there. Minus 19 minus 30. So I say, okay, bring down my 1, multiply, add, multiply, add, multiply, add. So we know that it's a factor. All right, so now I know that I have x plus 3 and x squared minus 3x minus 10. Well, that will be an easy one to factor. Since the leading coefficient is 1, you don't really have to go through that whole trash can method, although of course it will work. All right, but in this case we're going to get x minus 5 and x plus 2. So that means my remaining zeros are x equals 5 and x equals negative 2. Done. All right, is x minus 1 a factor of this absolute mess here? Justify your answer. All right, well, now, do we want to use synthetic division? If we did, I would put 1 in my box. I would put 10. Then I would have, 93 zeros. And then I would put a 5. And then I would have a couple more zeros. I guess this would only be 92 zeros. And then I would have 2 zeros after this. And then I would have a negative 7. and that synthetic division would take years, all right? Well, if x minus 1 is a 0, all right, then f of 1 has to equal 0. I'm sorry, if f minus 1 is a factor. Slip right there. All right. I guess the best way to do that. If x minus 1 is a factor, then x equal to 1 is a 0. All right. So the easiest way to do this is just plug 1 into here. So 10 times 1 to the 99th power plus 5 times 1 to the 6th power minus 8 times 1 cubed minus 7. 1 to any power is 1, so this is just 10. This is just 5. That's just minus 8 and minus 7. So this is 15. This is minus 15. Boom. So yes. Right. And all of this work is your justification. Much better than doing synthetic division with, 100 different things. Okay, the rational zero test. Right, if the polynomial f of x equals a sub n times x to the n, this is just standard form. Don't let that complicate things. Right, standard form of a polynomial. If it has integer coefficients, so if all the numbers in front of your variables are integers, right? Not fractions, not decimals, right? Integers, right? Then every rational zero has the form p over q, all right? And we have to be careful here. Well, I want that in here. Where p is a factor of a sub 0, and q is a factor of a sub n. All right, so this is very important to write there. So find the possible rational roots of f of x equals x cubed plus x plus 1. All right, well, we know that p's have to be the root of factors of 1. Well, what are my factors of 1? Just positive and negative 1. All right, the q's have to be the factors of my leading coefficient, all right, which is also 1, so plus or minus 1. Right? So if you take all of the possible q's divided by all of the possible q's, or possible p over q's, right? Well, 1 over 1 is 1, negative 1 over 1 is negative 1, and then of course those are the only other ones you're going to get. You don't have to repeat them, right? So this is it. We are done. Pretty straightforward and very easy when your constant term at the end and your leading coefficient are 1, but the bigger they get, the more factors they have and the more complicated it can become. All right, so what type of zero is shown on the graph? Okay, now it is important to note that these are only rational zeros. Okay, rational numbers are numbers that can be expressed as a fraction. 1/3, 2/7, 103 over 162, okay? Anything like that, all right? So, be very mindful that there can be other zeros that are not rational. Irrational numbers are numbers that cannot be expressed as fractions, okay? The most famous one, of course, is pi. We'll talk about another one next unit. All right, so I don't want to spoil its name, but we'll talk about another irrational one. Square roots of numbers that are not perfect squares are always irrational. The square root of 2, the square root of 3, the square root of 5, right? The square root of 6, the square root of 7, the square root of 8. Those will all be irrational. Basically, an irrational number is any number written as a decimal where the decimal never repeats and never ends. Okay. So do keep that in mind that it's, these only find rational zeros, not irrational. All right, so it says what type of zero is shown here on the graph? Well, I know that for my rational roots, my p over q's, all right, this is 1, this is 1. So again, it's just going to be plus or minus 1. Well, since negative 1 is here and positive 1 is here, and obviously this 0 is not positive or negative 1, all right, then we can say that this 0 is irrational, because the only rational solutions that this function can have are positive or negative 1, and this is not positive or negative 1, therefore it must be irrational. All right, so find the rational zeros of this. Okay. Well, first we need to find our possible rational zeros, which are our p over q's. All right, our p's are all of the factors of 3. So plus or minus 1, plus or minus 3. Our q's are all of the factors of 2. Because we're going to be doing p's over q's, you only need to take the plus or minuses of the p's or the q's, not really both. All right, so this is going to be 1 or 2. Those are the only factors of 2. All right, so that means our possible rational roots. Now, these are just possible ones. It doesn't mean that they all are or that they have to be. It's just ones that are. All right, so 1 over 1 would be 1. Negative 1 over 1 would be negative 1, so plus or minus 1. Same thing with positive 3 and negative 3 over 1. That would give me plus or minus 3. Positive 1 and negative 1 over 2 would give me plus or minus 1/2. And positive or negative 3 over 2 would give me plus or minus 3/2, right? Just this divided by this divided by this, right? This divided by this divided by this, so on. So obviously all of these can't be, because there's 8 possible rational roots here. Well, this is only a third degree polynomial, so at most there can be 3, okay? Well, how do we test? Because it actually wants us to find the rational zeros. All right, well, to test, we can use synthetic division and use the rational root theorem. The remainder theorem, which basically says if the remainder is 0, right, then we know that that thing is a factor. So all we have to do, plug these in using some synthetic division. So let's first try 1. It's the easiest, right? So we have 2, 3, negative 8, 3. So we bring this down, we multiply, we add, we multiply, we add, we multiply, we add. Sweet. So we know that 1 is a 0. All right. Well, now, honestly, since this was a cubic, I know that f of x is now equal to x minus 1 times 2x squared plus 5x minus 3. Now, you could have just kept testing these, right, using synthetic division. But once you get down to a quadratic, you can really just factor, right? So again, I can use my trash can method. 2 times negative 3 is negative 6, and 5. All right, so what numbers multiply together to give me negative 6, but add together to give me 5? How about 6 and negative 1? Right, 6 times negative 1 is negative 6. 6 plus negative 1 is 5. I keep my leading coefficient of 2, so 2x plus 6, 2x minus 1. I can factor a 2 out here. That leaves me x plus 3. Can't factor anything here. I throw away that out. All right, so now this factors to x minus 1, x plus 3, and 2x minus 1. So this will give me x equals 1. This will give me x equals negative 3. And this will give me, if I set this equal to 0 and solve, add 1, divide by 2, 1/2. Right? And are these all possible rational roots? They sure are, right? Positive 1/2, negative 3, positive 1. We're good to go. All right, so some other tests for zeros of polynomials. All right, so we know that an nth degree polynomial function can have at most n real zeros. We talked about that in our last lesson. All right. Of course, many nth degree polynomials do not have that many zeros. Right? That just means that they don't have that many real zeros, which means they would have some imaginary or complex solutions. All right? For instance, f of x equals x squared plus 1 has no real zeros, and f of x equals x cubed plus 1 has only one real zero. The following theorem, called Descartes' rule of signs, sheds more light on the number of real zeros of a polynomial. Right, so this is Descartes' rule of signs. Again, don't let this up here mess with you. That's just a standard form of a polynomial function. Right? It does say, though, it does let us know that to use Descartes' rule of signs, right, that we have to have a constant term at the end. Right? Like we have to have plus 5 or minus 2. We can't end with a 2x, right, for example. All right, the number of positive real zeros of f is either equal to the number of variations in sign of f of x or less than that number by an even integer. The number of negative real zeros of f is either equal to the number of variations in signs of f of negative x or less than that number by an even integer. Again, this can be a little bit confusing, all right, especially the or less than that number by an even integer. That just has to do with the fact that complex solutions come in pairs, all right, but we'll go ahead and look at an example that's a little bit easier when we do that. Okay, so describe the possible real zeros of f of x equals 3x cubed minus 5x squared plus 6x minus 4. All right, so first we're going to talk about possible positive real zeros. All right, so we just look at the number of sign changes. So we started positive, all right, then we have a negative here, we have a positive here, and we have a negative here. So how many times did we change signs? Well, we changed once from positive to negative, we changed again from negative to positive, and we changed again, right? So here's one change, here's two changes, here's three changes. So as far as positive real zeros, we can have 3 or 1, right? This is where that, in the last slide where it said, or less than that number by an even integer, basically whatever the number of sign changes are, you keep subtracting 2 until you get to 1 or 0, right? Obviously, you can't have negative solutions. Right, well now, to do possible negative real zeros, we have to look at f of negative x, which means we plug a negative x everywhere where there's an x. All right? If a negative x is raised to an odd power, the negative stays through, and it's going to change my leading coefficient. If we plug negative x into an x with an even power, all right, the x is just going to disappear, and the leading coefficient is going to stay the same. So because this is odd, my leading coefficient will change. Because this is even, my leading coefficient will stay the same. Here, this is odd to the first power, my leading coefficient will change. And then a constant never changes. That's kind of the meaning of the word constant, right? All right, so here I start negative, I stay negative, I stay negative, I stay negative. Well, it never changed. There were 0 changes in sign, so there cannot be any negative real zeros. Okay, now we kind of have to combine these to talk about the total real zeros. All right, well, if we have 3 positives and 0 negatives, we would have 3. If we have 1 positive and 0 negatives, we would have 1. Okay, so there's either going to be 3 or 1 real zero. All right, we'll go ahead and do both of these. All right, so first we'll look at 3x to the fourth plus 5x cubed minus 6x squared plus 8 plus 3. All right, so I'm going to do this one in red. So everything in red will have to do with that first function. All right, so possible positive real zeros. All right, how many sign changes do I have? I start positive, stay positive, change to negative, there's 1. I change to positive, there's 2. I change to negative, there's 3. So I can have 3. Remember, I have to keep subtracting 2 until I get to 1 or 0. So, or 1. All right, now I want to talk about possible negatives. In order to do that, I have to look at f of negative x. Remember, basically you keep all of this the same, but if I have an even x, my coefficient sign stays the same. If I have an odd powered x, my coefficient sign changes. So this is even, so it will stay positive 3x squared. This is odd, so it will change to negative 5x cubed. All right, this is even, so it will stay to negative 6x squared. This is odd, so it will change to negative 8x. And then I still have a minus 3. All right, so how many times do the signs change here? I start positive, I change to negative, so there's 1 change, stay negative, stay negative, stay negative. So there was only 1 change. So there's only 1 negative real solution. All right, well, now let's look at the total. Well, if I have 3 positives and 1 negative, that would give me 4 solutions. If I have 1 positive and 1 negative, that would give me 2. Those are the only possibilities. All right, for my second function here, I will do it with blue. All right, so my possible positive real solutions. All right, first, all right, I see how many times my sign changes. I start positive, I change negative, there's 1 change. I stay negative, so there was only 1 change. To look at my my possible negative real zeros, I have to look at f of negative x. So again, wherever I have an odd exponent, my sign changes. Wherever I have an even exponent, my sign stays the same. Here's odd, so that will change to a negative 2x cubed. Here, this is even, so it will stay negative 4x squared. And here, I just have minus 5. It's constant, it never changes. All right, so how many times do my signs change? I start negative, stay negative, stay negative. So there was 0 changes. So how many total real zeros will I have? Well, if I have 1 positive and 0 negatives, I can only have 1. All right, so that is it. All right. This just combines everything. All right. I'm going to go ahead and skip that. This is actually like very in-depth and detailed. All right. I won't have you do that much work on a test because it would take so long. All right. So we'll stop there. Of course, your homework will be on Delta Math. And like I said, this will be really everything that we need for this next unit test. Like I said, very short unit. So your review will be posted today. And then you'll have all day Thursday to work on the review, and I'll also post the solutions to the review on Thursday as well, and then your test will be on Friday.